Okay, so hello everyone. Welcome to this session, part of the Climate Adaptation Research Symposium. Our session will be on refining our ability to measure the social cost of carbon. My name is Ji-Sung Park. I'm at UCLA and I'm the Associate Director of Economic Research at the Luskin Center. We have a really awesome lineup of cutting-edge research and research economists presenting their research on this in this session. Let me start just by quickly thanking our sponsors and all the staff who put in an amazing effort to hold this conference virtually. And thanks to all of you for joining us. You should be able to use the controls if this setup is new to you, to minimize or maximize either of the screens that you see. If you have a question for the presenters, please click the question icon and type your question in. And as the moderator, I will ask those questions to the presenters once they're done presenting. And without further ado, I'm going to pass it over to our first speaker, who is Tamara Carlton, who will be talking about how climate change affects mortality. Tamma, you want to take it away?
Great, thank you. Thanks so much, everyone, for being here, and thanks for the invitation to speak today. I'm at UC Santa Barbara, and this talk is a collaboration with many of my colleagues at the Climate Impact Lab. We're a multi-institution collaboration focused on measuring the social cost of carbon using bottom-up empirical estimates. If anyone sat in on Sol Shung's talk earlier, a lot of these slides might look somewhat similar, and I'm hoping for those of you that see both of these, you get a picture of how we're trying to build up estimates of the social cost of carbon going sector by sector through the economy. So today we're going to be talking about energy in this session. So as many in this room are probably very familiar with, the idea of building a social cost of carbon depends really heavily on what's called the damage function. And you're seeing some example damage functions in the upper left here, where they relate the total share of GDP that is lost due to a given amount of warming on the x-axis. And these three damage functions come from leading integrated assessment models, DICE, Fund, and Page, that currently sit behind the US social cost of carbon and are also used abroad. And these have been really fundamental both in research and in policy, but they've increasingly come under scrutiny, particularly for their empirical foundations. So if you look on the right, this is a histogram of empirical studies that sit behind these damage functions, and we can see that they're relatively outdated and they're sort of few and far between. And so we want to work to improve these damage functions using the best available empirical evidence. And today we're going to be talking about energy, and one of the reasons to start here is that it's been hypothesized that energy demand, in particular cooling energy, as the climate warms, may be one of the most important components of the social cost of carbon. This quote here is from the developers of the Fund Integrated Assessment Model, hypothesizing the really important role of energy in the overall social cost of carbon. And what you're going to see throughout this talk is a sort of theme about the role and importance of income. And these slides just sort of get you thinking about the importance of accounting for and modeling economic development when thinking about energy consumption and climate change. If we're facing warmer temperatures in the future, and we're looking at incomes like Delhi, India today, we might be thinking about turning on a fan, potentially using some air conditioning. But if we're thinking about a future under warmer temperatures, under incomes like Dubai and the United Arab Emirates, we might be thinking about increasing demand through having an indoor ski slope and going skiing on a very hot day. And so which of these worlds we're in is going to be very important, thinking about the impacts on energy consumption, both across space and importantly, over time as economies grow and develop as climate change unfolds in parallel. So what we do in this paper is provide the first estimate of the global impact of climate change on total end-use energy consumption. And importantly, we're going to do so accounting for that role of economic development and other adaptive behaviors. So we're going to use these results to compute what we call a partial social cost of carbon. Again, if people saw Sol's talk earlier, he was looking at a partial social cost of carbon for a different sector of the economy. Here we're thinking about the net cost up to global energy consumption that's associated with one additional ton of CO2. But what we're really after here is adding up these partial social cost of carbon estimates across different sectors of the economy. We've got a working paper that's public on mortality where you can see what this looks like for another sector of the economy. So what we're going to go through today is first, we're going to go to the historical data and estimate the relationship between climate and energy consumption, importantly accounting for the role of income and other forms of climate adaptation. Then we're going to predict response functions at high resolution around the world that model adaptation both across space and across time to generate impacts of the impact of climate change in the future that accounts for those adaptations. We'll then estimate an empirical damage function, draw out something for energy that looks like that figure I started at the beginning of the talk with, and then use that damage function to compute a social cost of carbon that just pertains to energy consumption. So let's start at the beginning. We're going to pull together comprehensive energy consumption data from the IEA. This is covering 146 countries over more than 40 years. And these data are total end-use energy consumption across the residential, commercial, and industrial sectors. And we're going to collapse these data into total consumption of electricity and total consumption of other fuels, where our observational unit now is going to be a country in a given year for one of these two energy sources. We will combine these energy consumption data with high-resolution climate data to estimate a variant on the standard panel fixed effects model. The idea here is that we want a relationship between energy consumption and temperature, but we want that to vary based on conditions in a given location. So what that looks like is our outcome variable, E, here on the left-hand side, is total end-use energy consumption in country J for fuel category C in year T. And this is a flexible function of temperature, you see here, but this function F linking temperature to energy consumption will itself depend on the income in a given location and the average climatological conditions. Here, the climate is captured by average cooling degree days, which capture your exposure to heat, and average heating degree days, capturing your average exposure to cold. We control flexibly for precipitation, and then a host of fixed effects that allow us to isolate plausibly random year-to-year variation in the temperature that's experienced in a given country. There are some data inconsistencies in the IEA data. If anyone has ever worked with these, we're really careful to address all of those, importantly using reporting regime fixed effects, which ensure that the time series within any given panel unit is composed of energy consumption that's internally comparable through that time series. So what does this look like in the data? Let's first focus on the role, again, of economic development, which is really crucial to understanding this relationship. What you're seeing on the right is the response of electricity consumption to daily average temperature in the richest decile of our sample. And we see this strong U-shaped relationship where electricity consumption rises on cold days for used for heating and also rises on extremely hot days used for cooling. And this U-shaped relationship probably looks familiar to many people in this room. We've seen this recovered in the US, in the EU, and in many other wealthy locations where data are readily available. But what's important is when we move to slightly poorer parts of our global income distribution, the shape of this relationship really changes. So we see a U-shaped relationship still, but it's much more muted in these slightly poorer deciles of the global income distribution. Importantly, when we go to the poorest parts of the global distribution today, we see a virtually flat relationship between electricity consumption and daily temperature. For most of the global population, electricity consumption is virtually insensitive to daily temperatures because populations literally don't have the income to exploit the heating or cooling technologies that we enjoy when we turn on our AC or our heaters. Of course, this is important when we're thinking about the global cross-section today, but even more important as we think about populations moving through this space as they get richer, both in the sample and into the future. So here, these little white dots at the end represent a projection of income growth by 2099 under a socioeconomic scenario called SSP3. And so we want to think about populations moving through this space with their sensitivity of electricity consumption dramatically changing over time. This story looks somewhat similar for other fuels consumption. If we move to the richest decile in the lower right of our population, we see increases in other fuels consumption on cold days. These fuels are used for heating. But again, the sensitivity declines as we move to poorer and poorer parts of the sample. Importantly, we do see more of a response at these sort of moderate incomes. If you look in the middle of the screen, some of the moderate income levels, we do see increases in heating on these cold days, whereas for electricity, this relationship remains very flat. So what we're going to do is flexibly model this relationship, both with income, as you're seeing here, and with the long-run climate, allowing the shape of these two response functions to vary based on how wealthy a location is and what its average climate is. In the interest of time, I'm not going to get into the role of climate, but that's because this story is really about income. We see in the data that the role of average climate in shaping these response functions is quite minimal, whereas, as you can see here, income really strongly determines how sensitive either other fuels consumption or electricity consumption is to a hot or a cold day. So now that we have this model that allows us to estimate differential response functions based on the conditions in a location, we're going to go take that model and predict response functions at high resolution both today and into the future, so we can generate climate change projections that account for that heterogeneity and adaptation. To do so, we're going to start by dividing the world into a set of what we call impact regions that are standardized units of analysis in projections. These are designed to amalgamate political units, so they can think about them like a county in the US, for example. And they're comparable across themselves in population size, internally comparable in terms of their, internally homogeneous in terms of their climate. And then we're going to interpolate those responses you just saw into every impact region using the income for that impact region as well as its average climate. Just to sort of put in perspective what this means, a lot of the original IAMs that have been giving us our estimates of the social cost of carbon to date have been relatively coarse resolution. So DICE gave us estimates of total global damages of climate change. FUND, we get 16 different regions around the world. And what we're going to be able to do here is provide really high resolution estimates of the impacts of climate change, which also is important for modeling heterogeneity once we add this all up into the social cost of carbon. So these 25,000 regions, this is what it looks like when we project our response functions onto those 25,000 regions. So what you want to think about here in terms of the color is the height. The color indicates the height of that response function on a hot day, 32 degrees C, relative to a moderate day at 20 C. And these dark red locations are the places where we really see high sensitivity to those hot temperatures. And those are largely the wealthiest locations in the world. This is given the covariates of today, so at our climate and our incomes of today. In much of the rest of the world, we're seeing either a very minimal response, a slight decline in these regions that are blue that is statistically insignificantly different from zero. However, when we move forward to end of century, this map looks very different. So as most populations dramatically increase their income growth under SSP3 in this case, we see that most regions of the world now have a high sensitivity in terms of their electricity demand on a hot day. Although it's still very muted if you look in sub-Saharan Africa or in India, many regions of the world don't get sufficiently rich that they really see that steep U-shaped relationship you saw prior in the talk. So everyone looks red now, but we still do see that some locations are so poor that we're still not seeing high sensitivity of electricity demand. This looks somewhat similar for other fuels demand on a cold day at end of century. Most places have gotten rich enough where they're increasing other fuels demand on a cold day at end of century. But again, the poorest regions of the world have statistically insignificant effects. These are largely zeros in most of sub-Saharan Africa or in India. So what those maps tell us is sort of the shape of that response function in different regions of the world. And what we want to be able to do is take those response functions, combine them with a set of climate models to project the total impacts of climate change. But we want to be really careful here because I just told you that economic development really changes the shape of these response functions. So we want to compute the impact of climate change, netting out other factors that are going to change in the future. So the way to think about this is that India is likely to grow, their GDP per capita is likely to grow in India by 2099, whether or not climate change unfolds. And we expect that that income growth will imply that people have more air conditioners and use more air conditioning. There's going to be increased use in electricity on hot days, regardless of whether climate change unfolds or not. So the projections that I'll show you today will be the difference between two scenarios. If you look at the bottom of this slide, the first scenario is a richer world that does experience climate change, but we subtract off a counterfactual where we have a richer world, but climate change doesn't unfold. And that ensures that what we're showing you here is just the role of climate change, not the parallel trajectory of income and its role in changing electricity demand. So what does this look like? Here you're seeing the change in consumption due to warming under a high emission scenario, RCP 8.5, by end of century across these 25,000 regions. And this is a mean effect across the distribution representing both statistical and climate model uncertainty. Of course, we see a strong latitudinal gradient. So Many regions of the world on net are seeing an increase in electricity demand due to an increase in hot days. But if we go to the coldest regions of the world, we see a decline in electricity used for heating as the climate warms. To try to get a sense of these magnitudes, let's go to the US. On net, the US impact from warming, even under this high emission scenario, is just 2% of current consumption. So that blue bar represents total current consumption, and you can barely see this little gray bar representing the delta due to climate change. This looks very different in poorer regions of the world. So if we go to India, the increase in electricity consumption represents over 100% of current consumption. And this, again, is representative of other developing countries where, largely because current consumption is so low, the increase in electricity demand does really represent a massive change in total electricity demand. When we look at the consumption of other fuels, this map looks much more basic. Everyone is saving energy, right? So because this is sort of an L-shaped response function, we're seeing savings of other fuel demand under climate change uniformly around the world, although of course the magnitude is much lower in the poorer parts of the world. The story in magnitudes, again, is similar. In the US, this represents a really modest change in other fuels consumption relative to today's total consumption, whereas in a place like India, this is a more substantial share of total consumption by end of century. So those tell you at high resolution total impacts on electricity and other fuels consumption, but we're really after the social cost of carbon, particularly in this session. That's what we want to talk about. And so to get there, we're going to go through an empirical damage function. So let's use these results to compute an empirical damage function. The first step in doing that is to turn those gigajoule impacts into monetized impacts. Of course, there's a lot of sensitivity analysis done on this in the paper. What you're seeing here is the average monetized impacts, assuming current prices grow at a 1.4% annual price growth. That's historically observed price growth. We show in the paper many different price scenarios, and qualitatively these results are very similar. Even quantitatively, they're bounded by a very small range. So what you're seeing here, where the world looks mostly blue, that means that in monetized value, those savings of other fuels are outweighing those increases in electricity consumption, and we're on net saving money in terms of our expenditures on energy consumption when you add up electricity and other fuels consumption. There are a few regions of the world where you see these slight yellow colors, which are sometimes statistically significant, sometimes not. But in most regions of the world, on average, we're saving spending on energy consumption by end of century under this assumption of price growth. What these little distributions highlight for you is that this is an average, but for each one of these regions, we estimate a full distribution of the impacts where that distribution represents both statistical and climate model uncertainty. And that full distribution is going to be really important when we want to turn this type of impact into a damage function. And that's what we're going to do here. So again, a damage function relates monetized damages to total amount of global warming. So what we do is we take each one of the realizations from those distributions you just saw, and we index them against the total amount of warming from that particular climate model, and that draw the statistical uncertainty. And so you see here, these are climate model realizations for RCP 4.5, and the y-axis is the total spending change across the entire world, summed across those 25,000 regions. When we add in RCP 8.5, we can fill out this distribution, filling out the support of amounts of warming we see by end of century. And we estimate a damage function through these points, as well as uncertainty, which we show in the paper. And what's sort of interesting here, this is not the case that we've seen in other sectors. This is a very strikingly linear damage function. And because it's linear, we can summarize these impacts really, really simply. So for about 1 degree increase in warming, we see that electricity consumption is rising about 6% of current global consumption. Other fuels consumption is falling about 6%. This nets out to a small decline in the total monetized value of 1 degree of warming in terms of energy consumption. So now that we have a damage function, we want to turn that into a social cost of carbon. And so what we do is we use what's called a simple climate model. We're using the FAIR climate model. And that climate model allows us to pulse the atmosphere with just 1 additional ton of CO2, which you're seeing here in panel A. That turns into a change in atmospheric concentrations that obviously is dynamic over time. So this goes out to 2300. That change in concentration translates into a dynamic change in the temperature anomaly. And if you think back to that damage function figure, that's moving us along the x-axis of our damage function, that temperature anomaly change over time. And so through the damage function, we then get a present value of the damages in every single year due just to that pulse of CO2. The social cost of carbon, as I'm sure we're all aware, is the net present value of these damages. And so when we add those up for RCP 8.5, we get savings of about $1. So this means that increasing CO2 by one ton is going to lead us to saving of about $1 when you consider both the change in electricity and other fuels consumption and integrating over years until 2300. And this is under a discount rate of 3%, assuming a price growth rate of 1.4%. Again, we can look at different discount rates, different RCPs, and in the paper, we do a host of different alternative future price scenarios. These are pricing scenarios where we assume a certain rate of price growth, or where we go to the energy model IAMs and pull out different trajectories of pricings from other IAMs. And we still really see a very narrow bound in this estimate, somewhere from savings of about $3 to savings of about 60 cents, regardless of these different sensitivity checks. So the overall story of modest savings due to a ton of CO2 sort of holds up against in all these different sensitivity checks. So just to sort of summarize where we've been, what I've shown you is an example of this bottom-up approach that we're working to develop, where we build partial social cost of carbon estimates for individual sectors of the economy. We find that for energy consumption, this amounts to savings of about $1 per ton of CO2 under a 3% discount rate. Importantly, this accounts for adaptation and the role of income growth. And just to build some intuition, this isn't necessarily the number that we would have guessed a priori, and maybe others in the room are surprised by this number as well. The real intuition for why we're seeing this modest decline is a very nonlinear relationship between income and the shape of the temperature-energy relationship. So that's what we saw at the beginning. And this means that many regions of the world are simply too poor to increase energy consumption in response to climate change. Even by the time we get to 2100, we're seeing many parts of the world that are just not that responsive. For those that are responsive, we see these emerging economies that are growing quite a bit by 2099, increasing electricity, but there's many wealthy, colder economies that are saving other fuels and also sometimes saving electricity. And so these really balance each other out such that this end result is a small negative number. And just before signing off, I want to highlight that this result that we've found in this ongoing work at Climate Impact Lab is leading us to believe that building an empirically based social cost of carbon could really have first order policy implications. What you're seeing here is a comparison of our current estimates of the social cost of carbon for energy on the left, mortality in the middle, as compared to fund, which is one of the IAMs sitting behind the current social cost of carbon. You're seeing that in blue. So in energy, we're seeing that we have a small negative, fund gives a quite large positive estimate. In mortality, the answer is reversed. We have a quite large positive estimate and fund has a very minimal positive estimate. And indeed, for mortality, we see that this effect is a good share of the overall social cost of carbon across all sectors that was used in the Obama administration. And so we're really excited to keep adding these sectors together and working on integrating them such that we can improve our overall estimates of the social cost of carbon really from the bottom up using a data-driven approach. Thank you all so much. I'm happy to answer questions and follow up offline if anyone is interested.
Great. Tamma, thank you. That was an excellent presentation and really surprising results in some ways. I do have to start. Let me start by apologizing. I mischaracterized the talk. I said temperature and mortality. I had in my mind another equally awesome talk that you gave very recently on that subject. Members of the audience, if you have questions, please do type them into the question box. Let me lead us off with a question, Tamma. You know, as difficult as this is going to be to execute empirically, I'm wondering if you could comment just a little bit about how we should think about technical change. So, for example, I'm thinking about, you know, how should we think about these results in a world with and without a directed policy effort at trying to bring down the cost of air conditioning, for example, for poor individuals in India, Brazil, where have you. I know that's very hard to model and estimate empirically, but if you could just give us some intuition about how to think about the results. Yeah.
Great question. So if you think about the model that we have estimated, the type of technological development or change that we do account for is only that which is correlated with income. So to the extent that that income is driving that process, we are capturing it and we are allowing incomes to evolve out of sample into the future such that that energy sensitivity will evolve into the future into ranges that we haven't seen historically. But what you're talking about is more directed technical change that may not be correlated with income at all. So the only thing that we do try to tackle this in the paper, and I'd be super interested to see if people have better ideas. But what we do is we add to this model, in addition to income, a simple time trend interacting with your sensitivity. So this allows, in the historical sample, for us to see if just time evolving over time over our sample changes sensitivity to temperature, even when you condition on income. And we do, in fact, see that that's the case, both for electricity and other fuels consumption. So then what we do is we take those estimates of the role of time on the response function and project them into the future. That's a huge assumption to swallow because it's a linear extrapolation. We're assuming that, you know, the huge increases in AC that we've seen in the US, for example, might increase the same way in the future. And that's one of the only things that we've done to this SCC that does really change the magnitude. And we do get a more substantial social cost of carbon estimate. You know, we're still not anything like our mortality estimates, for example, but you can sort of bite off those big assumptions. You can model them into the future. We do see this number changing, but the main reason a few reasons I'd feel really uncomfortable sort of taking that as a main estimate is that linear extrapolation of time trends, of course, but also that kind of implies that you see technological change that increases demand, but doesn't also increase efficiency because you're still increasing electricity by the same amount per unit of demand on a hot day. And so I think, you know, there's some really interesting questions about how those two things would evolve in the future that maybe beyond the scope of this paper, but yeah, great question.
Awesome. Let me do one quick question from the audience. How does infrastructure play a role in the variables of the equation you presented? This is from Yvette.
Energy infrastructure. Yeah, that's a great question. So presumably, I think probably two answers. So one, I'm not exactly sure what the main concern of the question asker is, but one concern that we had is if you see a big change in a country's time series of other fuels consumption, for example, when there was a substantial change in the energy infrastructure of a country. So a really big investment in a new plant or something that really changed the nature of that time series. And that was one of the reasons I highlighted that we were controlling for really big jumps in those time series based on potential changes in infrastructure that would conflate our estimation. I think maybe that wasn't that was one worry we had. I'm not sure if that was the concern of the question asker. And in terms of any other changes in infrastructure that might change your shift between, I wish I could follow up and ask this question, ask me more what they're asking. I think probably my answer is similar to Jisung's in that we use income as a proxy for many things. So if the nature of infrastructure was changing such that the temperature sensitivity of electricity or other fuels was evolving over time in a way that was not correlated with income, we would be missing that channel. And so we would be missing that channel. If you have forecasts of how that might change into the future, we would definitely be missing that channel to the extent that as countries get richer, they invest in similar types of energy infrastructure over time. I would say that we are capturing that, but we're relying really heavily on income, largely because that's what we have forecasts for in the future. But I apologize if I wasn't quite getting what the question asker was really after there.
I think that's a great response. All right. Thank you very much, Tamma. Let me now pass it over to Ishan.
Great. Thanks. Can you hear me, Jisung?
Yep.
Cool. Do I just keep going until I get to mine?
Yeah, I guess this is Tamma's appendix.
Oh.
Here we go.
Oh. Oops. Oh, okay, great. Hi, I'm Ishan. I'm a postdoc in economics at the University of Chicago. Thanks so much to everyone for organizing this conference, and especially to Jisung for inviting me to be here. This is my paper, The Food Problem and the Aggregate Productivity Consequences of Climate Change. So I'll start with my motivation, which I think will be familiar to a lot of people in this audience, which comes from this large empirical literature projecting the impacts of climate change on agricultural productivity. And basically what we know from this work is that in general, extreme temperatures are bad for crops and moderate temperatures are good. So hot parts of the world are likely to see steep declines in agricultural productivity, while cooler places at higher latitudes are likely to see neutral or even positive effects as they warm. This underscores how critical it is to know where the world's farms will be in the future. When you look at this map, it's clear that climate change will be really, really bad in poor countries if they continue to specialize heavily in agriculture. But maybe it would be a lot less bad if we moved a lot of farms to Canada and shipped more food to India. So that's basically my research question. How will climate change affect the distribution of labor between agricultural and non-agricultural production across the world? And what are the welfare consequences of this reallocation that we expect to happen in practice? So there are two necessary conditions for this grow more food in Canada hypothesis to hold. The first is that for Ricardian comparative advantage in agriculture to shift away from the equator, what we need to know is the change in the relative productivity of agriculture. We have evidence from other work that extreme temperatures also affect productivity in other sectors, so the change in agricultural productivity isn't sufficient alone to know how comparative advantage is changing. I addressed this question empirically using firm-level microdata from 17 countries covering about 60% of the world's manufacturing output to estimate the relationship between extreme temperatures and productivity in manufacturing and services. So this gives me the answer to the first part of the question, in which I'd find that indeed comparative advantage, not just absolute advantage in agriculture, is indeed likely to move away from the equator. But there's a second necessary condition for this grow more food in Canada hypothesis to hold. Specialization in agriculture must actually follow comparative advantage. In practice, what we see in the world is that poor countries actually specialize heavily in agriculture despite very low absolute and relative productivity. So the stylized fact is that the richest 90th percentile countries, countries at the 90th percentile of the income distribution in the world, are about 4 times more productive than the poorest 10th percentile countries in manufacturing, but they're about 45 times more productive in agriculture. So if specialization followed the Econ 101 Ricardian comparative advantage story, even without climate change, we'd expect to see basically nobody farming in poor, hot countries and everybody in the United States working on farms. So it must be that something more complicated is going on here. So to address this part of the question, I write and estimate a model that captures this existing pattern of specialization in the world, and then use that model to simulate the impact of climate change on labor reallocation across sectors, trade flows in food and non-food across the world, and welfare in 158 countries. So why do poor countries specialize in agriculture despite being really bad at it? This phenomenon is what the macro development literature calls the food problem, and what I argue is central to understanding the general equilibrium effects of climate change. The idea is that because food is a necessity for people to survive, when people are poor and the relative price of food is high, the quantity of food consumed can't fall too much, so food ends up taking up a large share of expenditures. Consumption has to come from somewhere, so all else equal, a higher consumption share also tends to raise agriculture's production and labor shares. Now, in principle, countries could meet their consumer needs for food by importing more food, but in practice, this channel is very weak in developing countries. So the stylized fact here is that the average person in the poorest quartile of the world consumes about 91% domestically produced food, compared with about 45% in the richest quartile. So my model is going to capture these two competing effects on sectoral reallocation in response to an agriculture bias decline in productivity caused by climate change. On the one hand, as climate change makes people poorer and raises the relative price of food, it'll tend to raise the expenditure share in agriculture and push more labor towards farming. That's the food problem. Then on the other hand, there's this Ricardian effect shifting comparative advantage that will tend to push countries to raise their imports of food and push exports and production towards other sectors. So ultimately, the labor reallocation is going to be a horse race between those two effects, and it's not clear a priori whether we can expect declines in agricultural productivity in poor countries to decrease or actually increase their specialization in agriculture. So that's a summary of what I'm looking at in my paper. Now I'll try to show you results from the two sections of the paper. So the first part of the paper, I'm going to free ride a little off the criteria that Tamma laid out for what we want in these empirical estimates of the relationship between temperature and outcome variables, which in this case, we want to be able to project the impact of climate change on non-agricultural productivity. And to do that, we want to use data from around the world. We want to have some methods to get at plausible causality in the relationship between temperature and productivity. And we want to account for both the costs and benefits of adaptation. So this is a summary of where my data comes from. I mentioned that it's data from around the world. And another thing that I'll mention about it is that my data goes from the 1st to the 90th percentile of the world's temperature distribution in the global cross-section, and the 3rd to the 99th percentile of the world's income distribution. So I have a good range of hot and cold and rich and poor countries, so I can try to get at whether this effect differs across places. Similarly, not shockingly, similarly to my co-author Tamma, my regression specification will model firm level output per worker, revenue per worker at firm I in year T as a function of the temperature that that firm experiences contemporaneously in that year. And then, of course, I have my firm fixed effects and country by year or state by year fixed effects in different specifications to try to isolate the within firm variation in temperature and get the causal effect of temperature. And then I interact that causal effect of temperature with a proxy for how productive that firm and that country is, its GDP per capita, and the long run average temperature experienced by that firm, with the intuition being, and I show in the paper that this is consistent with the firm's first order condition, the intuition being that we expect firms that are more productive and more used to certain extremes to make more investments to adapt to them. There it is. And what this specification allows me to do is to predict temperature sensitivity anywhere in the world as a function of these two readily available variables, how rich and how hot that place are, which we also have projections of into the future. So I don't have data from Algeria in my paper, but my model requires me to make projections in Algeria. And this specification is going to allow me to know what the temperature, or to estimate what the temperature sensitivity is in Algeria, both today and into the future. So this graph shows the main results from my estimate of this regression specification on my data. And so what we're looking at here is how extreme temperatures affect manufacturing revenue per worker across the world's income distribution going up and across the world's temperature distribution going left to right. I'm not actually sure if people can see my mouse pointing, but this bottom middle cell here, what that represents is the relationship between temperature and firm level revenue per worker in a poor country of a moderate in a poor country of a moderate temperature. So what we can see here is that an extremely hot day or an extremely cold day in this hypothetical Franken country, which is poor and has average temperature, will reduce annual output per worker by about 0.4 percentage points, which is approximately equal to zeroing out one whole day's productivity if you assume 50-week, 5-day work week calendar. So what we can see is that temperature has really large effects on output in poor countries. But the other thing we can see in this graph is really strong evidence of adaptation. So as you move up the rows, the impacts of extreme temperature become substantially more muted in the richer places. And as you move to the right, the effects of extreme heat become more moderate in places that are hotter. And similarly, moving to the left, the effects of extreme cold are less in places that are colder and therefore more used to that type of extreme. So now I've estimated these effects. And thanks to the climate scientists, we know how temperatures are going to change, or we can predict how temperatures are going to change around the world. And so I take my estimated temperature sensitivities from the last slide, and I just project them all around the world based on countries' present and future projected incomes and temperatures. And as we saw on the last slide, we know that colder places and poorer places are more susceptible to extreme heat. Then I combine those temperature sensitivities with global climate model projections of the changes in temperature that we expect places to realize. And what I find is that particularly in some developing countries, we can expect some pretty substantial impacts of climate change on manufacturing productivity in like double-digit percentage points. But also that if you remember, the initial goal of this section that I laid out was to figure out the relative productivity impacts between agriculture and manufacturing. So the impacts in manufacturing are not small, but the impacts in agriculture are very large. And so when I combine these results with the agriculture results that I showed you earlier, what I find is that the change in the relative productivity in agriculture is qualitatively similar to the change in the absolute productivity in agriculture, because the effects in other sectors are somewhat smaller. And so it is actually true that the comparative advantage in agriculture is likely to shift away from the equator. Okay, so that's the first part of my paper. Now I have these sector by country level estimated productivity impacts, and I need a model to understand how they're likely to affect reallocation across sectors and welfare. So I'm just going to lay out an overview of my model, which combines the standard features from models in the structural transformation and trade literatures. So there are three sectors in my model: agriculture, manufacturing, and services. And consumers have these non-homothetic preferences such that agriculture takes up the largest share of your expenditures when you're poorest, as we observe in the world. And then within each sector, there's going to be a continuum of producers that each draw their productivity from an aggregate sector by country productivity distribution. And the parameter that governs this sector by country productivity distribution is where my empirical estimates will feed into the model. So there's a parameter that's like aggregate, the average manufacturing productivity in India or the average agricultural productivity in Canada. And those are the parameters that my empirical estimates are going to move around in the climate change simulations. Agriculture and manufacturing are traded in my model, as they mostly are in the world, and services are non-traded. And for the traded sectors, I estimate trade costs that vary at the importer-exporter sector level. So there's some cost for shipping food from India to Canada, some different cost in the model for shipping manufactured goods from India to Canada, and then two other costs that I estimate for shipping from Canada to India. And then in the model, wages adjust to aggregate productivity such that you have comparative advantage in the sectors with relatively high productivity, because those sectors will face wages that are low relative to the costs that are low relative to their productivities. So I'm going to spare you most of the equations in my model, but I do want to show you one equation because I think it's critical to understanding the intuition that I was building up in the introduction. So in the model, the labor share in agriculture, there's you can derive this equation for the labor share in agriculture as a function of the expenditure share in agriculture. That's this XAK, and then basically net exports in food. So the pi AKK is the proportion of your own food that you produce in your own country. And then the second term is adding up the food that you export to all the other countries across the world. And so if you lived in autarky and it was only your country, the second term would be 0. You wouldn't ship any food anywhere else. And this first pi would be 1. You would produce all of your own food at home. And so what this model allows us to do is break down that horse race I was talking about in the introduction. So when you introduce this agriculture biased productivity shock into the model, because of the food problem, as people get poorer and the price of food rises and people are still having to buy food, the share of spending on food goes up. So this XAK is going to rise. So all else equal, that'll mean that the labor share in agriculture rises when agricultural productivity falls, which of course, intuitively, that's not great if more people are moving into the sector where productivity is falling a lot. But then the rest of this horse race is coming from the Ricardian effect, which is as your relative productivity in agriculture falls, that'll tend to make imports of food more attractive and exports of food less attractive. And so you tend to see countries import more food and export less food, at least to the extent that they're open to trade. So I break down this model in the I break down this horse race in the equations, but now we want to see who wins the horse race in the simulated model with the climate change impacts. So I estimate the parameters of this model, and I simulate a baseline version of the world, and then I introduce my climate change productivity effects into the model to see how these variables change. And what this picture shows you is my predicted simulated impact of climate change on net exports in agriculture. And so what this tells you basically at a high level is that the change in agricultural net exports goes the intuitive Ricardian direction that we would expect. The hotter countries in the world are getting relatively worse at agriculture, and the colder countries are getting relatively better. So we do expect to see in the model some more exports of food from Sweden and Norway and Canada, and some more imports of food in the hotter countries of the world. But one thing to note about this graph is that the numbers are pretty small. Most of them are around 1 to 2 percentage points as a share of GDP. And so this reallocation of trade in the current world is pretty limited in the model simulations, such that when I calculate the net impact of this horse race between the food problem and trade, and in most of the poorer, hotter countries in the world, the food problem is kind of winning the race, so to speak, such that the net impact on the agricultural share of the labor force is projected to be that in the poorest quartile of the world, I predict that the agriculture share of labor actually rises by about 3 percentage points in response to the climate change productivity effects. And so returning to the intuition of it, I told you guys in the introduction that the poorer parts of the world are mostly pretty close to trade. And that's where these agricultural productivity shocks are likely to hit hardest. And since the trade effect is more muted, but people still need to eat food, it ends up pushing more people into the sector that produces food to meet these subsistence requirements. So this is a summary of my results, my baseline model results, in which I introduced the impacts of climate change and tried to calculate these impacts on reallocation and welfare. So we can see that for the poorest quartile of the world, about 3 percentage points more people are projected to work on farms due to the impacts of climate change. And the willingness to pay to avoid these productivity effects of climate change is a couple of percentage points of global GDP, but that's heavily concentrated in poor countries, which are willing to pay almost 10% of their income to avoid these productivity impacts of climate change. And the mechanism for that is these increases in the price of food across the world, especially highly concentrated in poorer countries, where, of course, if agricultural productivity is falling a lot and they're mostly dependent on domestic agriculture, the price of food rises a lot in these model projections. So to drive home the importance of the key policy point in these model counterfactuals, I run an alternative simulation with this hypothetical world that's a lot more open to trade. And so what I do in this low trade cost counterfactual is I just reassign the trade barriers. Instead of giving the level of trade barriers that I estimate to match the trade flows we actually see in the world, I just give all of the countries about the 90th percentile level of trade openness. So I assign all of the TAUs, all of the trade costs of my model to a level that's typical of what we see in like the OECD countries that are fairly open to trade. The reason I don't assign it to 0 is because I want this to be a realistic counterfactual. We don't want to wish away the fact that it's expensive to ship stuff across the world to people who speak a different language. We just want to say, suppose we could achieve a level of trade openness that we know some countries have already achieved in the world. And then I re-estimate all of my climate change simulations to compare this hypothetical world that's more open to trade to the world that actually exists in the first simulation. And so this table shows a summary of the results from this exercise. And what we can see is that the low trade cost scenario modestly reduces the willingness to pay to avoid climate change for the entire world from about 1.7 to 1.3% of global income. But it has especially large effects for the poorest quartile of the world. So in the low trade cost scenario, the willingness to pay to avoid climate change is about 70% lower, 65 to 70% lower for the poorest quartile of the world. And the critical mechanism for that is illustrated in this last column, which is the change in food prices, both for the world and for the poorest quartile. So the change in food prices driven by the climate change productivity effects is, first of all, smaller overall in the second scenario because we would expect the agriculture to be more efficiently reallocated across the world in response to the change in productivity in the scenario with greater openness to trade. And critically, it's more evenly shared across the world. So in the first scenario, that's the real trade cost one, or the estimated trade cost one, food prices especially rise in poor countries because domestic shocks are going to be are going to hit domestic consumers when they're reliant on domestic production. But in the second scenario, where consumers are consuming a more globally diversified basket of food, if you get a bad productivity shock domestically, it doesn't hit the prices as badly. And the increase in food prices is going to be more shared across the world. So that's a quick summary. That's what can fit into 15 to 20 minutes about my paper. Just to reiterate it, I find in the first part of my paper that extreme temperatures can have pretty large effects on non-agricultural productivity, but there's strong evidence of adaptation such that rich countries and countries that are more used to certain extremes have smaller impacts on the non-agricultural sector. And then in my model simulations, I find that climate change is likely to exacerbate the food problem and keep more people stuck on farms in poor, hot countries where agricultural productivity is falling a lot, unfortunately. And then in my simulations, I find that under current policy, trade does little for climate change adaptation, but that freer trade could, at least plausibly, dramatically reduce the damages of climate change in poor countries. So thanks for listening, and I'll be happy to take any questions.
Fantastic. Ishan, that's great. I'm probably not the last to say that it looks like a lot of careful work went into this, and it's a really great paper that illustrates, how climate change is a problem that interacts with so many other policy challenges, right, including international trade. Again, in the audience, if you have questions, please do type them into the question box. I have one here from Samantha who asks, it seems like the analysis went all in on temperature changes. Do you have plans to consider changes to other climate variables that may be relevant to agriculture? For example, precipitation, moisture, evaporation, or humidity? Also, I may have missed this, but do you just use one climate model scenario, or do you use an ensemble to examine any uncertainty in temperature?
Great questions. The answer to the first question is in the agriculture results that I pulled from the literature, they do actually consider a variety of climate variables. I'd have to look back at exactly what it was, but definitely precipitation, irrigation, temperature are in there, and soil. I think something about soil quality also. I don't remember the full list. And as a robustness check, eventually related to Tamma's presentation before me, there's in the pipeline a project about agriculture. And so I plan to have a different set of agricultural productivity estimates that I feed into my model from our own work in progress eventually when they're ready, which also will cover a different variety of climate variables and their impact on crops. The answer to the second question is that just due to feasibility and the number of moving parts in the paper, for now, I only have one climate model. I tried to make it a climate model that was both representative, kind of a median estimate of global temperature change across the climate models. And importantly, it's one of the climate models that was used in the construction of the agricultural productivity results I'm using right now to try to achieve consistency across the sectors and the projections. But if there's particular concern, I could run it with a couple more. I think running it with all 33 is a little too much for me to do by myself.
Great. I think we have time for one last quick question. How should we think about what would happen in a future in which developing countries grow, urbanize, and boost agricultural productivity? Does your low trade cost scenario capture some of this?
Yeah, that's a great question. So in the paper, I didn't have time to cover this today, but in the paper, I have a section where I look at projections of future income change. And one of the things that we can project with future income change is that agricultural productivity would be rising is one of the things that drives the income change, and also that specialization in agriculture decreases as countries get richer. And so both of those things will reduce the cost of climate change, the productivity cost of climate change, at least globally and in those countries in particular. So in the presentation, I focused on trade policy as one of the things that could really help us adapt to these climate change agricultural productivity effects. But in the paper, I do also mention that the model shows pretty clearly the importance of economic growth in general, and these mechanisms for economic growth with rising agricultural productivity and urbanization are really critical to insulating us from the costs of climate change. So I think that question's totally right. And if you want to look at the draft that's online, it's in section 7.6 where I talk about that.
You don't remember which page though, Ishan, do you?
I don't, sorry.
All right, thanks again. Let me now pass the mic over to Danny.
Great, thank you, Ji-sung. Here, oh, good. No appendix slides on that one. Hey, my name's Danny Bressler. R. Daniel Bressler is my official academic name. And I'm a fourth-year PhD candidate at Columbia University. This is the mortality cost of carbon. So just briefly, I only have 18 minutes to discuss a pretty long paper here. So I'm going to give you a high-level overview, high-level gloss of what I did. But if you want all the details, it's available as a working paper with Columbia's Center for Environmental Economics and Policy. Just came out around a month ago. Okay, so to start with some, there's clicks on this one, nice. Okay, just to start with some motivation for why I did this. Tamma mentioned this earlier, but essentially the social cost of carbon and integrated assessment models that produce that social cost of carbon, it's well known that their damage functions are using old studies that are outdated, and they're also leaving out a significant portions of impacts that the peer-reviewed literature is suggesting is likely to happen. So in 2009, a Lancet report concluded that climate change is the biggest global health threat of the 21st century. There have been hundreds of recent scholarly papers that have suggested that global warming is likely to have a significant mortality effect. But this literature is not accounted for, this recent literature, in the most widely used integrated assessment models. So in DICE 2016, for instance, mortality costs account for less than 5% of climate damages. And in the 2017 National Academy of Sciences report on the social cost of carbon, they specifically mention mortality as a damage source that could be immediately updated in integrated assessment models. So as you can probably guess, that's exactly what I did. So I made two major contributions. The first is that I extended DICE, which is an integrated assessment model created by William Nordhaus. He won the Nobel Prize in Economics 2 years ago, in large part for working on this model. So I extend this model to include the impact of climate change on human mortality. And this extended model is called DICE EMR, which stands for DICE with an endogenous mortality response. And this has two major implications. One is that it revises the optimal emissions path suggested by DICE. So essentially what this model does is it compares the benefit that you get from reducing emissions with the cost that you get from having to reorganize your economy to decarbonize the economy. So weighing those two things, it determines an optimal emissions path. So I revised that optimal emissions path. The second thing is it revises the social cost of carbon in the model. We've been talking a lot about that in the other presentations. Okay, the second major thing I did, and perhaps a little more originally, is that I estimated a new metric that I introduced in the paper. And that metric is called the mortality cost of carbon. And this is the expected number of excess deaths globally that are caused by the emission of 1 additional metric ton of carbon dioxide equivalent emissions in 2020. In the second half of the presentation, I'll go over that in a lot of detail. So let me give you a preview of the results. So as I mentioned, optimal climate policy is revised. On the left-hand side, what you see here are the emissions trajectories under different sorts of scenarios. So the red line on top, this is the emissions trajectory in the baseline DICE scenario. So this says if we do very little to combat climate change, we're going to continue to increase the total amount of emissions on a global basis through the end of the century. And the warming effect of this, that's on the right-hand chart here, it's going to be over 4 degrees Celsius of warming by the end of the century. Then, as I mentioned, DICE also has a suggested optimal climate policy, and that's the blue line here on the left-hand chart. So essentially what's being suggested by DICE is that we should roughly plateau our emissions at about 40 gigatons of carbon dioxide equivalent per year, and we plateau that through 2050, and then we really only start decarbonizing after 2050 in the latter part of the 21st century. And then the result of that, in terms of the increase in global average temperatures, is that we get to 3.5 degrees Celsius by the end of the century. So essentially what this is implying is that the 2-degree target that was agreed to with the Paris Agreement, we want to make sure that temperatures don't go over that. That's what the international community agreed to. DICE is suggesting that that's wrong, that it's too expensive to do that. It would be better to let temperatures rise to 3.5 degrees Celsius. So then after I incorporate the effects of mortality in DICE EMR into the DICE model, you can see that on the green line here on the left-hand side. So it's much faster decarbonization in the optimal climate policy, and then full decarbonization by 2050. And then the emission or the temperature effect of that is that the temperatures stay just below 2.5 degrees Celsius by the end of the century. Okay, and then the other result is the social cost of carbon. So in the original DICE 2016 model, the 2020 social cost of carbon was $37 per metric ton in the baseline scenario. And then after we put in these mortality costs, the social cost of carbon in the baseline specification in the baseline emission scenario, that's in bold here, is $265 per metric ton. So it increases by a factor of 7. Okay, so let's talk about how I did this. There's a lot of pages in the working paper that talk about this. I'm only going to give you a very high-level gloss here. But the left-hand side, this shows the original DICE damage function. Tamma showed this earlier in her presentation as well. But essentially, it's just a reduced form representation for increases in global average temperatures. You lose a percentage of global output as a function of the increase in global average temperatures. So in the original DICE model, this equation represents the only way that climate affects the economy. Everything is supposed to be included in this original damage function. And as I mentioned, it turns out that the effects of mortality are largely not accounted for in this original damage function. So that what I do is the right-hand side here. So I take the original damage function from the DICE model, but then I add a new source or way that the climate affects society, which is what I call a reduced form climate mortality response function. So this just says, as a function of increases in global average temperatures, what is the percentage increase in the mortality rate? And then I do this by doing a review of a bunch of different studies, including a very good study from Tamma and Ishan in the Climate Impact Lab to estimate what this function looks like. So this function is essentially just estimated from the empirical literature that makes projections. Okay, so I'm going to skip over this. It's a little too technical and it'll take me too long. You can read about it in the paper. But let me talk about how I chose the studies that I ended up using to project this mortality response function. So these criteria are quite similar to what that Tamma and Ishan both mentioned, but I'll mention it briefly because there's some differences. So one is that I need the studies that I use to project the human mortality impact in terms of excess deaths or in terms of an increase in the mortality rate as a function of global average temperatures, or such that I can back this out quite easily. So that's one thing I need. It just needs to make a numerical projection. The second is that it should be as comprehensive as possible of the human mortality impacts caused by climate change. The third goal was to find studies that present mortality estimates net of the effects of defensive adaptation. So as we've been talking about throughout this conference, people are going to make investments to reduce the mortality effects that climate change has, such as buying air conditioning. So the studies ideally should account for that. Fourth, the estimates need to be aggregated globally. As Tamma mentioned earlier, this is a global model. It's essentially a one-region model, and the region is the globe. So I need estimates that I can work with. So of course, there's going to be a lot of regional heterogeneities in terms of the mortality impact, and the studies that I use account for that. But then ultimately, I need to use the aggregated global projection to get this single mortality response function for the whole globe that can fit with the DICE model. And then finally, the papers just need to be published relatively recently. They need to be published in the last 20 years, in the 21st century, essentially. So I was already aware of the Climate Impact Lab paper by Tamma and her colleagues going into this, but I wanted to make sure that I was systematic and went through all the other literature that was available and make sure I wasn't missing anything. So I read through 100 different papers. There's a long methodology for how I did the systematic research synthesis you can read about in the paper. But I discovered some other papers that were useful, and I used them to project the mortality response function. One is this first paper here from 2014. That's a World Health Organization paper. It's actually really an agglomeration of 6 different papers that look at different mortality pathways and then aggregate them into a single global projection. So I used that paper from the World Health Organization. I used this paper from the Climate Impact Lab that it sounds like Tamma presented relatively recently to the GSUNG that he mentioned. And then I used another paper from Antonio Gasparini and his colleagues in the Lancet. That was another study that I used. So I use these studies to project that mortality response function. You can read a lot more details in the working paper since I have limited time to discuss it here. Okay, so let me discuss the mortality cost of carbon. And let me start with giving you sort of a motivation for why I thought about this in the first place to do this. The first is that imagine that we could solve these issues with the way that integrated assessment models are currently calculating the social cost of carbon, right? Imagine that we had updated studies that weren't old, and imagine that we could account for all of the different sources of impacts. Okay, imagine we could do that. There would still be 2 fundamental issues. One is that a wide variety of climate damages, they must be monetized and then summarized into a single number, and the relative contribution of these damages is often unclear, especially in the DICE model when you just have the single reduced form damage function. And the second is that the magnitude of climate damages, it's quite sensitive, and the social cost of carbon is quite sensitive to subjective choices around how you choose to monetize non-market damages. And since these damages are occurring over a long period of time, the discount rate at which future value is then converted into present value. So you'd still have these issues. So this got me thinking, in large part, what's contentious about the social cost of carbon is, one, this discount rate. How do you discount future value relative to current value? And it turns out the social cost of carbon is very sensitive to this. So depending on what discount rate you use, there's a big debate in the mid-2000s between Nicholas Stern from the UK, and William Nordhaus about which discount rate to use. And the ultimate social cost of carbon you get is really sensitive to that discount rate. And two is how you value non-market damages, in particular lost human lives. So how you choose to weigh the value of continued life against consumption. And not only that, how you choose to value life in different parts of the world. So the standard way to do it in the literature is to do this value statistical life, which essentially looks at the willingness to pay to avoid a little increase in the probability that you die, right? But that's heavily sensitive to your income. So if you're in a place with low income, such as sub-Saharan Africa, you might have a value of statistical life that is, 1/50th of what it is in the United States. So if you're looking at a global model with a bunch of different value statistical lives in different areas, and most of the deaths are happening in low-income areas, you might have a very different answer for your social cost of carbon than if you use a different methodology. In my particular paper, because I only have one region, I'm using the DICE model, everyone is valued at the global average value of statistical life. And there's a lot more details on that in the working paper you can read about. So anyway, but the general point here is that, there's good arguments to be made about, how you choose to answer these different types of questions. But the social cost of carbon is very sensitive to how you choose to answer those types of questions. So I thought, why not just present the marginal damage from emissions in terms of the actual value before you monetize and then discount those damages. And in the context of human mortality, this means just presenting the number of excess deaths from marginal emissions. That's exactly what the mortality cost of carbon is. So it's the number of expected excess deaths globally over the next 80 years caused by the emission of one additional metric ton of carbon dioxide equivalent emissions in 2020. So it's similar to the social cost of carbon in that both metrics, they quantify the damage from a marginal increase in emissions in a certain year. But there's three important differences. The first is that the social cost of carbon, it includes all market and non-market impacts from marginal emissions, whereas the mortality cost of carbon only measures the effect of marginal emissions on excess deaths. Two is that the social cost of carbon monetizes all climate damages into a single consumption equivalent value, whereas the mortality cost of carbon does not monetize damages because it's just in units of excess death. And third is that the social cost of carbon converts future damages to present value through discounting, whereas the mortality cost of carbon, it's just simply the number of excess deaths over the next 80 years. And you can disaggregate when these deaths happen, and that's an exercise I do in the paper, and I can talk about here. So, I think it's a useful supplement, and this is important. We still need the social cost of carbon. It's very important for policy because we need to know what the optimal carbon tax is, the optimal Pigovian tax. But as I mentioned, discounting and valuing lives is a complex and controversial issue. So it's useful to also just present the marginal projections that we're making without discounting or valuing those lives. And that's exactly what the mortality cost of carbon does. And then finally, I think it's also useful for informing decision-making of individuals and organizations whose emissions are quite marginal compared to the overall global economy. So for instance, there's charities that try to look at how can you save the most lives at the lowest possible cost. One of my favorite organizations, GiveWell, they essentially are trying to answer this question. So if they could know if you reduced carbon emissions and that had some effect on reducing excess deaths, that would be quite a useful figure for them to know. So that's another use case for this thing. Okay, so what is the mortality cost of carbon? So in the DICE baseline scenario, which results in over 4 degrees Celsius warming by 2100, the 2020 mortality cost of carbon is 2.35 times 10 to the negative fourth lives per metric ton. So when I first calculated that, I'm like, I have no intuition for what that really means. So what does that imply? It implies that 4,262 metric tons of 2020 emissions, they caused one excess death from 2020 to 2100. And again, I didn't really have great intuition for how much 4,262 metric tons of emissions is. So I tried to convert it into something that I had better intuition for. So 4,262 metric tons, that's equivalent to the current lifetime emissions of 3.3 average Americans. So if you were to take the current lifetime emissions of 3.3 average Americans, you were to put them up into the atmosphere right now in 2020, that would cause one excess death globally over the next 80 years, according to DICE EMR. And there's other ways you could look at this too. I'm going to skip over this in the interest of time. You can read about it in the paper. So this chart just shows how that metric that I just discussed varies in different places. And this is just simply a function of how the average carbon intensity of the economy varies in different parts of the world. So if you took, as I mentioned over here on the right, the lifetime emissions of 3.3 Americans, if you were to put that in the atmosphere right now, that causes one excess death. On the world average, you took the average world citizen, it would take 12.3 lifetime emissions emitted right now to cause one excess death. But then if you look in a place like Nigeria that has much lower per capita emissions, it would take 140.5 Nigerians, lifetime emissions of that many Nigerians to cause one excess death. So that just shows you how this kind of varies. So, when I first did this, I'm like, wow, this is really big. I was kind of surprised by it. I was trying to figure out what was going on here. It's surprisingly large, especially compared to the total effect. The total effect is just saying, okay, look at the effect of all emissions from all global economic activity in aggregate across time. So just saying, how many excess deaths are due to global warming. And the total effect in DICE EMR is 89 million projected cumulative excess deaths over the next 80 years in the baseline scenario. Again, that results in just over 4 degrees Celsius by the end of the century. But then this marginal effect is like massive, right? It's like 3.3 lifetime emissions of Americans. You emit that on the just in 2020, and then you cause one excess death. There's 330 million Americans. So then how could this be? Clearly, there's something that's not linear going on here, and that's kind of the answer. This is, again, you can read about this in the paper, probably a little too technical, but let me try to give you some intuition here. So this is just the curve from DICE EMR that shows the number of yearly excess deaths as a function of the increase in global average temperatures, right? And when you think about what a marginal emission, like a pulse of 1 ton of carbon dioxide does, essentially what it does is that in every year going forward, you're going to slightly itsy bit, that's a technical word, itsy bit, increase the temperatures by a little bit in every year going forward, right? So the question is, how damaging is that? As Tamma mentioned earlier, the carbon dioxide stays around for a long period of time in the atmosphere. 100 years in the future, you still have 1/3 of that original emission left, roughly. So what's really driving this marginal effect is the first derivative of this here. So if you just increase global average temperatures by a little bit, how many extra deaths are you creating? And what this implies is that as long as we stay below 2 degrees Celsius, the first derivative is pretty shallow. The mortality cost of carbon is going to be pretty small. But in the scenario, this baseline emission scenario where we're getting to 4 degrees Celsius, this first derivative is quite steep. So little marginal change in temperature is going to have a significant mortality effect. So that's really what's driving this large mortality cost of carbon, especially in this baseline emission scenario. So this curve that I just showed you on the left-hand side here, that's just a function of me just summarizing essentially what this other literature was projecting, and it took a lot more probably work for them to do those projections that took me to put all this together here. But intuitively, why is this so large? Why is it the case that curve is so convex? And I think there's 2 key reasons that have been discussed throughout this conference. One is that a pervasive finding in the literature is that extremely hot days are especially severe. And there's, in terms of their effect on mortality, there's a big nonlinear effect there. And there's important physiological reasons for that. And then 2, the expected number of extremely hot days is expected to increase roughly exponentially in global average temperatures. So you're really increasing this number of hot days, and those hot days are really damaging. So that, I think together, those 2 things intuitively kind of explain to me at least why that mortality response curve was so convex. So there's sort of a silver lining to this, and that's that it implies that if we avoid going into these dangerous areas where, for instance, we get to 4 degrees Celsius or higher by the end of the century, there's a potential for a significant mortality benefit. So this left-hand chart, this is just what I showed you before, showing for instance, the number of Americans that causes 1 excess death over the next 80 years if you were to release all their emissions at once, right? So now let's imagine, instead of getting to that baseline scenario, we did the optimal emission scenario, and we had just under 2.5 degrees warming by the end of the century. Now it would take the lifetime emissions of 6.8 Americans released in the atmosphere right now to cause one excess death. So there's a significant benefit when we avoid these kind of dangerous, like 3, 4, or 5 degrees Celsius scenarios. And here's another way of seeing that. This is just the cumulative number of excess deaths as a function of time in different scenarios. So the red is the baseline scenario. So you have 89 million cumulative excess deaths by 2100 when you have over 4 degrees warming by the end of the century. If you're able to stay on this optimal path and keep it below 2.5 degrees Celsius, then you only have 19 million cumulative excess deaths by the end of the century. You're essentially saving 70 million lives, or reducing 70 million excess deaths by taking that policy. So there's a few, I'll go over these really quickly, Ji-sung. I know I'm a little over. These clicks are killing me. So there's just a few I'm just going to mention these briefly. You can read about this more in the paper. Some limitations, caveats. This only represents mortality through the pathways that are included in the reports that I use. And arguably, there's some mortality pathways that are left out. I talked about that in detail in the paper. Another is that people have mentioned that, and this is important, there's co-benefits of stricter climate policy. So there's a really good paper by Noah Skowronek and his colleagues that came out recently, and they noticed that if you were to take aggressive policy in terms of reducing carbon emissions, you also reduce, for instance, the emissions from coal-fired power plants, and you reduce the harm from particulate matter, which is a significant public health harm. So that's another thing that is not accounted for in this paper, but in the future you could imagine us combining models to capture that. Another thing is I don't directly model the costs of adaptation in this paper. In theory, the original DICE damage function is supposed to account for that, but I did a review you can read about in the paper that concludes that the costs are probably understated in that original damage function. And then finally, I just want to emphasize, I'm taking the DICE model as it exists, and I'm just putting on the effects of mortality. Other people, for instance, this recent paper by Hansel that just came out, look at other issues with the DICE model that you could argue should be changed. I'm just looking at the effect of mortality. So you should think about this optimal emissions trajectory as like the definitive optimal emissions trajectory, just what you would get in DICE if you added in this mortality effect. So just to wrap up here, 2 important takeaways. One is that when you incorporate mortality costs into DICE, this drastically changes the suggested optimal climate policy, and it brings it closer to international targets set by the Paris Agreement. And then 2, the mortality effect of marginal emissions is surprisingly high, especially in high emission scenarios, due to the high degree of convexity of mortality increase in global average temperatures. And then that has 2 important implications. One is that marginal changes to emissions in these baseline scenarios have substantial effects on future mortality through climate. And then also avoiding scenarios where the mortality response is effectively steep, so above 3 degrees Celsius, 4 degrees Celsius in particular, those have a significant mortality benefit. So thank you very much, and looking forward to chatting.
Great. Danny, thank you. That's really interesting paper and a great talk. One thing that strikes me is just how much all 3 of these papers seem to illustrate, how the gap between the research frontier and policy application is, or at least we're aspiring to try to close that. That's certainly a motivation of the symposium. I know Tamma had a question for you. Tamma, I can read it or you can ask it. It's up to you.
Yeah, I can just ask it.
Sure.
Daniel, that was really great. That's super exciting work. I was just wondering about the dependence on socioeconomic projections of total population, because while I agree the SCC is controversial because of its dependence on the discount rate and on the valuation scenario, it seems like you're equally dependent on projecting how many people live on the planet where, which is also sort of fraught with all sorts of forecasting challenges.
Yeah, that's a great question. So the way that I project population into the future is I use the 2019 UN disappeared. I just had an appendix slide on it. But I use the UN population prospect central estimate. And so, if you imagine that populations are going to be 2 billion, I think it projects around 11 billion by the end of the century. But there's significant uncertainty about that. So you could run sensitivities with different projections in terms of the population projection.
Yeah, it might be good to do that just because we tend to think about the discount rate being a key source of uncertainty that we want to capture. And then it'd just be good to see how sensitive your results are to those scenarios. But very cool.
Mm-hmm. All right. Any other questions from the audience? So there was one question from before during your talk, Tamma, that I didn't get a chance to ask. I unfortunately don't have the exact wording here, but it was something about asking you to sort of comment on why it was that you focused on energy consumption. And my immediate thought is, well, the Impact Lab is focusing on a whole suite of impacts, but I'll let you tackle that. And maybe since we have some time to describe that broader agenda, since it is a nice way to sort of tie in all of the material that we've talked about today.
Yeah, sure. I responded to this person individually, but I think the format is such that everyone can see that. So I made that point at the beginning of the talk because in prior work, it was hypothesized that energy demand may be one of the key components of the SCC. So in fund, it's a vast majority of the overall SCC does come from cooling demand. What we are finding is that doesn't seem to be the case when we update these numbers based on our best attempts to use the empirical evidence that we can. So I would not conclude that no longer do we think that that's the case, but that was sort of what was hypothesized prior. And in terms of building up the SCC at the Climate Impact Lab, we're sort of letting the best available evidence and data be our guide. So mortality has been a really well-studied area, as Daniel's work has highlighted, agriculture, energy, labor supply. So we're really trying to break off the sectors where we think there's good data, good methods have been developed. We kind of know a lot about that question, and that way we can really leverage it. But of course, the list of sectors that we want to add in is very long, and we hope to keep adding them in. But what we're trying to do is use existing evidence to break off the big ones first.
That sounds great. Let's see. We have another question here. So I believe this is for Danny. Did you look at the age-specific mortality and how sensitive the estimates are to an aging population, especially in the developed world?
Yeah, that's a great question. Yeah. So in the model, right now, it's just an increase in the number of excess deaths. Because the different studies I use, for instance, in Tamma's and Ishan's paper, they have 3 different age groups, I think, right? It's like 65 plus, 18 to 65, and less than that. The other papers I use don't break down. Is that right? The other paper. Oh, okay, yeah, you could correct it. The other papers don't break down, for instance, Gasparini, Hales in their central. Estimates don't break down by age group. So yeah, right now it's just looking at the number of excess deaths. There's a bunch of implications of that we can discuss and are talked about in the paper. But yeah, that's something that could be extended in the future, especially as there's more empirical estimates that I could use to construct different age-specific functions.
Great. So we have a couple of more minutes. Do any of the presenters have questions for each other? The presentations were so comprehensive. Danny has like a 50-slide appendix that we decided not to go into.
Yeah.
Well, go ahead.
Yeah, I wrote it down here. Oh yeah, Tamma, one question. You said 1.4% annual price growth. I assume that's real price growth, right?
Yeah. Yes.
Okay.
Yeah, and we look at 0% or 3%, and then we use energy models to pull out the price scenarios in those energy models, and it's just strikingly similar results across these. The main story really is the same.
Yeah, one of the reasons the price growth doesn't matter a lot is because it's applied to both the other energy, which is decreasing, and the electricity. So kind of cancels out.
Well, so one question I have with all 3 of you is I know, oh, hang on. Let's prioritize the questions from the audience. Oh, this is a request for Danny's email. I will send that Saturday. So one question I have for all 3 of you, since you've all been so involved in research that is trying to inform the social cost of carbon, which is again is this summary indicator, right? And this is for the non-economists in the audience. Summary indicator of just how bad climate change is going to be in terms of the effects on the economy and human livelihoods. Maybe asking you to take off your individual researcher hats for a moment and to engage in a little bit more speculative conversation. How, based on your work, and again, most of this was sector specific, but based on your work, how would you characterize just the broader evolution of our understanding of what the social cost of carbon is relative to, say, what is currently reflected in policy, and how we should think about that in the context of the current state of mitigation policy? I know that's a lot, but just if you have a couple of takeaways, since I know you've all spent so much time in this literature.
I mean, one high-level thought that's not that directly related to the literature is just we don't have carbon prices for like 60% of the world's emissions or more, or whatever it is. So the social cost of carbon is implied. The policy social cost of carbon is zero for a lot of things. We use it for regulatory impact analysis in the United States, but there's only so many things that are affected by federal regulations.
Mm-hmm. Anyone else?
Yeah, and as everyone probably knows, the Trump administration has drastically decreased what they think the social cost of carbon is, because they increased the discount rate to 7%, I think, instead of 3%, and only looked at damages in the U.S. So it's like $1.70, I think. Is that right? Just for the
it's about $1.07% discount rate. Yep, that's right. I think my only comment is the SCC is used in a lot of innovative ways at local levels and in other countries around the world. And so I think, sometimes people ask about working to update the social cost of carbon. We don't have a federal government that's about to implement it in any way that maybe lines up with the scientific evidence, but we're using it in many different ways. Not like Ishan said, we're not taxing emissions, but I think there's a lot of exciting ways to use this kind of work in ways you may not expect to use the social cost of carbon, or these type of impact analyses that Ishan is doing, that we're doing at the Climate Impact Lab for local level policy that is not necessarily the way we tend to motivate the overall SCC, but I think there's a lot of innovative ways policymakers are using them around the world, and we can hope that that continues sort of regardless of what federal policy happens in the United States.
That was a much better answer than mine, and I just want to officially retract my own answer and change it to an endorsement of Tamma's answer.
No, that's a really good point, right? I mean, there are certainly not only state and local governments, but also private corporations internally use the social cost of carbon for a variety of things. So it's absolutely an important dimension of the work. Great. Well, thank you again to all the presenters for awesome presentations. Thanks to everyone in the audience for attending. If you're interested in learning more about their work, you can find all the abstracts online, and I'm sure you can find the working papers that are available online, and when they become available to be shared through our lists. Okay, thank you again for joining us.